Okay, everyone, so welcome to your first recitation. My name is Ben. I will be your TA for the semester. Just so that you know, the cameras in the back are so that we can record this recitation for the 513 students. So the topic of today's recitation is data representations. So you've been talking in class. Well, actually, first let's talk about what recitation is. So recitation is a place where we can have a little bit more of an interactive learning session than lecture. So in recitation, if you ever have a question, raise your hand so that you can ask. That's part of the point of recitation. If you want to go over an example, a particular example of something that you talked about in class that you're confused about, ask about that, and we can go over that here. We'll cover a recap of stuff from class. We'll go over example problems that'll help you for your homework, for your exams. And we'll go over demos and tips and questions about the labs as they come out. So a little bit of course news. Hopefully you've seen most of this already. So we have a course website, cs.cmu.edu/213. That's where all of the important stuff for the course is, all of the schedules, all of the labs, everything can be linked to from there. You should have access to Datalab by now. That's how you'll actually be turning in the labs. If you don't have access to Datalab, you should email the staff list. That address is on the website. We have office hours. There's actually a typo in the slides there in Wien Hall 5207, not GHC. But the office hours will be every Sunday through Thursday, 6 to 9 p.m. And then we will also have additional office hours near the due dates. Both some of those times will be extended, and sometimes we'll have office hours on Fridays. And you should see the website for the exact schedule of when those extended office hours are. Also, this Saturday, we are having a Linux boot camp, 2 to 4 p.m. in GACE 4401. So the Linux boot camp is if you are feeling weak on your skills with like SSH or navigating a Unix file system. If you want to learn more about how to use a text editor like Vim or Emacs that you can use over SSH, we'll be covering all of that at the Linux Bootcamp because you do need to do your homeworks on either the Unix machines or the Shark machines. So this stuff will be important for you to be able to complete it. And also Datalab is due this Thursday, September 17th at 11:59 p.m. Hopefully you've all at least started on it. So today we're going to talk about a couple different things. The first thing we're going to talk about is Datalab and how you should go about doing that. And we'll talk about integers. We'll review some of the stuff you learned in class. And we'll review some of the floating point stuff you've learned in class. Okay, so Datalab. How do you do Datalab? First thing, you need to download the files from Datalab. So all of the lab files will be on Datalab throughout the semester. There'll be a tar with the C files and other executables and stuff in it, and then there'll also be a link to a PDF write-up on Datalab. And so you should read both of those. They both have information about every lab. Make sure that you're doing your labs on either the Andrew Unix machines or the Shark machines. For some of the labs, you'll have to use the Shark machines. The next lab, Bomb Lab, will only work if you're using the Shark machines. The Shark machines are special machines just for you guys, the 213 students and the 513 students. The login password and username is the same as your Android ID and password that you would use for the other machines. Make sure you don't untar the handout onto like your local Windows machine or something, because then it won't maintain the permission bits and you'll get all kinds of error messages when you try to run the programs. If you do happen to get those sort of error messages, in order to make a file executable, the command is chmod +x, the file name, and then you'll be able to execute the file again. Okay, so what you want to do for BitLab. So BitLab, what you have is you have a bunch of puzzles, and you have to solve this puzzle using a certain set of operations that are legal and not using more than a certain number of those operations. So there's 3 important programs that we have for you that will help you do this. So let's actually go on to the Shark machines and sort of try these out. So the Shark machine, you put SSH. Is that big enough for everyone to see it? So SSH, your Andrew ID, and then, oops, it's not capital R. It's shark.ics.cs.cmu.edu. And then the password will be the same as your Andrew password. Okay, so you can see there's all these different Shark machines. If you don't put which one in particular you want to be on, it'll just pick one for you at random and sort of distribute the students across them. They reboot early in the morning, so if you happen to be working on your work that early in the morning, just be aware that it might shut down in the middle depending on which one you are. So what we have here is, so I've downloaded the Datalab handout.tar from Autolab. And what you want to do is you want to untar it. And then what you get is it dumps it all into a directory named Datalab handout. So if you missed the command, that was tar xvf datalab handout.tar. That's in the handout. And so what you see is, so you go in here and you get a bunch of files. And some of these won't actually be in here by default because I've already started it. But what you get is you get these files in here. So the most important file here is bits.c. This is the file you'll actually be editing. So we can open it up. Oop, that's not it. Okay, so what we have is we have here a bunch of instructions. It's a bit smaller. So we've got a bunch of instructions on how to do Datalab at the top of the file. Make sure you read those. And then what you're going to do is you have all of these puzzles. So for each one, you have a certain set of legal operations. So here the first puzzle is bit XOR. So bit XOR, you're allowed to use the negation operator, bitwise negation, and bitwise and that's it. And you can use up to 14 of them in order to do the same behavior that XOR would do. So what you want to do is you want to go in here and you want to actually implement that. So say I decide I'm going to implement it by just doing X XOR Y, because like that's totally going to work, right? So I mean that does the same thing as XOR. We know it does. Okay, so I've done that. And now what? So now I can make. So make will compile your code, what you currently have. And what it'll do is it'll also now give you an executable called btest. So now I have the btest executable and also gave me these other two programs called fshow and ishow. So now I can run btest. So btest is the first thing we have. So we have three ways to test our solutions: btest, DLC, and the BDD checker. Btest is the first way to test your solutions. So what does it do? It says, okay, I got a score of 1 on bit XOR and failed all of the other ones. But what we know is that I actually didn't do bit XOR right, because I used an illegal op. So btest is just checking that the answer is correct, but it's not actually checking that I followed all of the invariants in the file. So we have a second program, which is the DLC checker. So the DLC is a special compiler that will check if I followed the invariants correctly. Oops. So I run it on bits.c, and what does it tell me? It tells me, oh, I used an illegal operator XOR, because that's not allowed in that puzzle. So if you're ever not sure if what you're doing is legal or not, if you want to make sure that you've used the correct number of ops, that you've only used the ops that are allowed, the DLC checker is the program that does that. And then also, we have driver.pl. So driver.pl will do two things. It'll run the DLC checker, and then it runs the BDD checker. So the BDD checker is the actual grading program that's going to be used by Autolab. Autolab uses driver.pl, the exact same script that you have here. So if I ran that, what it would tell me that I used an illegal operator in the first problem, and I got all of the rest of them wrong because I didn't do them. So right now I have a 0 out of 63. So there's a couple other things that these programs can do. So btest can do more than just run on the whole thing. You can also do a btest, and if we do -- help, we can see the different options for it. So we see that we can do btest, and we can give it, let's see, we can give it a function name. So if I give it bit XOR, oops, no, I didn't do it right, -f. So if we do btest and give it -f, and I don't know why my terminal is doing these weird things, and bit XOR, then it will run just on that function. So if we're just working on one function and we don't want to see all of the output for the rest of them, we can use -f. Now say we're working on it and we want to actually try it out on some particular values to see if it works on those, then we can do btest, we can give it a function, and we can do -1 and give it one argument, and -2 and give it another argument, and it will run it on those things and tell you if it passed on those or not. So my implementation does work for 9 and 34, which is unsurprising because it does just use XOR. So we could do the same thing if we reopen bits.c. Say now that I've realized from the DLC checker that this is not a legal way to do it, and so I'm going to try it just by doing this instead. I'll just bitwise AND them, because that's a legal op and it's less than 14 of them. So I do that, and then what we want to do is we need to remake so that we'll get recompile the program. Okay, and so now we can do btest on bit XOR. And it failed, and it gives me a counterexample of where it failed. So if we give it intmin and intmin, bit AND is not the same as bit XOR. But if we run the DLC compiler on it, we can see that at least I followed all of the invariants. So those are the different programs you'll want to be using. In addition, there's also two more. You can see two more programs in here, fshow and ishow. So fshow and ishow are utility programs to help you. So fshow, we can look at the help for it. Oops, that's not how you get the help for it. Well, it tells us the usage anyway. So you give it some values as either hex or floating point numbers, and it will tell you stuff about the bit patterns that those have. So if I give it 0, it tells me that the bit representation of 0 is just all zeros, that the sign, exponent, and fraction bits are all zeros, and that is a denormalized number. So this is useful for you once you get to the float puzzles if you want to know things about particular floats. We can do the same thing and say give it 1.5, and it'll tell us the floating point representation of 1.5. And then we also have ishow. So if we want to see some decimal numbers, we can see that 42 is hex 2a and is an unsigned and signed integer with value 42. Okay, so any questions about the Datalab programs and how you go about solving that and knowing if you're correct and checking your solutions as you go? No questions? Okay, good. So that's it for that, okay? And then the last thing you do once you've actually finished Datalab, or if you're partway through and you want to checkpoint your progress, you can submit to Autolab. You have to submit through the website. We don't have a check-in script like you might have had in 122 or anything. You just have to submit through the website. In order to get a tar file out of your files that you can submit to the website, that's the command you want to use there. And it should be in the handout too. Okay, so a couple other things about BitLab. So the DLC checker will check that you have used the correct number of ops, that you've only used legal ops. But it also has a couple different constraints. It's a modified compiler from MIT or somewhere that's like really old. And that means that it has some style guidelines that you have to follow that you wouldn't normally need for modern C code. So all of your variable declarations need to be together at the top of a function. So even if you don't use it yet, you need to put all of the variables declared before you do anything else. You need to make sure that the closing brace for the function is in the first column and that none of the other closing braces are in the first column. We won't be using this compiler for the later labs, so you just have to worry about this for now. In the future, you'll be able to write C as you normally would. Also, you should think about operator precedence and use parentheses to be very explicit about it. Does anyone know what the precedences of those things are relative to each other? I mean, why would you? Do you really even need to have that memorized? I think what it is the unary negation binds the tightest, and then times, and then plus, and then the bitwise shift. But maybe I'm wrong, and so use parentheses. They're free. You don't have a limit on the parentheses. It'll help you out so that you're not making mistakes by writing something down that is different than what you thought you wrote. You should take advantage of special operators if you're allowed to use negation. Use negation. 0 is a useful number. Int min is a useful number. You should try to work these into your puzzles. They'll help you out. And once you've gotten down to the required number of ops, using only the legal ones, you have full credit. If you want to reduce it more just to get higher on the scoreboard, you can, but you won't get any more points. Also, you should worry about undefined behavior. So shifting by greater than 31, bit shifting by greater than 31 bits or by a negative number of bits is undefined. Here's a little bit of an excerpt from the x86 reference about what shifting by more than 31 does. So it just takes those extra bits and it puts them into a flag, and whichever one happens to be the last one that got thrown away just ends up in the flag in the end. And then your program will execute differently if that flag is used somewhere later along the line. So you should worry about that and make sure you don't do stuff that's undefined. And there's some assumptions that you can make. In bits.c, it tells you about some assumptions you can make about the behavior. OK, so any other questions about Datalab? OK. So now we're going to do a little bit of a review from class. So you've been talking about data representation. And two of the things you've talked about are integers and floating points, right? They've talked about how we represent integers and floating points on modern computers. So integers are simpler than floating points. We have signed and unsigned integers. If we have an unsigned integer, then it represents the numbers 0 through 2 to the however many bits we have minus 1. And if we have an unsigned integer or a signed integer, then we can do from negative 2 to the number of bits we have minus 1 to 1 less than that in the positive, because 0 is a non-negative number. So a couple of the interesting things we can do with integers is use bit shifts to simulate multiplying and dividing. So multiplying and dividing are pretty slow on the actual machine relative to the other arithmetic operations. But bit shifting is really fast because you're just moving things left and right. So if we want to multiply a number by a power of 2, we can just left shift by that many bits. So why does this work? So if we have a number in binary, what does it represent? So we've got some number. And what are these? This is the bit that's 2 to the 0. This is the bit that's 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, and so on. And so a binary number is just like a sum of powers of 2. And so when we left shift, which pads with zeros, say we left shift by 1, then what we get is we'll have a 0 here, and then all of this gets pushed over. And what does that do? That means that this 2 to the 0 became a 2 to the 1, so it got multiplied by 2. This 2 to the 3 became a 2 to the 4, it got multiplied by 2. All of the 1s get multiplied by 2, so the new sum is twice as big, because this number is a sum of powers of 2. So does that make sense, how left shifting is the same as multiplying by a power of 2? Yes? OK. And then we can also do the same where we right shift to divide by a power of 2. But now it gets a little bit more tricky. So for positive numbers, the story is the same. We just right shift, and then it's the same as bumping them all down by whatever amount we want, and then we've divided by that power of 2. But what about negative numbers? What's the problem with negative numbers? This is on the slides, so. If you don't remember, you can read it and then tell me. What's the problem with negative numbers? It's going to round towards negative infinity, but we want the division to round towards 0, right? So say we have a negative number. So how about let's work with, let's see, I had an example. So let's try out, let's say we have a 4-bit 2's complement system. So what does that mean? That means we're going to have one sign bit and then 3 other bits, and that's how we're going to represent our numbers. So say we have the number, this marker is not good. Say we have the number 1010. And this is 4 bits, 4 bits, 2's complement. What's the decimal number that this is equal to? So in base 2, what's this in base 10? Does anyone know? 10?
Oh, sorry.
So this, yeah, so this is 2's complement, so this is a sign bit, so this is a negative number. I heard someone say it. -6, right. So how did we get -6? So I'm using this little subscript notation to note if I'm writing the number in binary or decimal. So 2 for binary, 10 for decimal. So yeah, how did we get -6? So the sign bit is 1. So when the sign bit is 1, that's a -8 because we have 4 bits here. And then this is a +2 that we've added back into that. So that leaves us with -6. And so like if we had a 1 here, that would be adding 1 more, and it would be -5. Okay, so we have -6. Say we want to divide -6 by 4. So we want to divide this by 4, and we're going to try doing that by just shifting to the right by 2, because 4 is 2 to the 2. So what do we get? So when we do an arithmetic shift, so there's 2 types of shifts that we can do, logical and arithmetic. And when we do a logical right shift, what that means is you just pad with zeros, the extra things that are showing up on the end. And that can be used to divide unsigned numbers. But since we're working with a signed number here, we want to do an arithmetic shift, which pads with the value of the sign bit. So when we have a negative number, it pads with 1s, and we have a positive number, it pads with 0s. So we do a right shift, arithmetic right shift by 2. And so what do we get? So we get 2 1s for the padding, and we have this 1 and 0 here. This is binary. So what number did we end up with? -2, right. So we ended up with -2. But what is -6 over 4 rounded towards 0? So rounded towards 0, we wanted -1, because this is equal to -3/2. We're rounding towards 0, so since it's right between -1 and -2, we round towards 0 as -1. This didn't give us the right thing. This truncated those extra bits, it just threw them away and rounded towards -infinity. So we need to do something a little bit more interesting, a little bit more complicated in order to divide a signed number that's negative just by using bit shifting. So the solution is something called biasing. So what we do, so biasing. So we want to add 2 to the k minus 1 to our number before we shift, where k is the number of bits we're shifting. So what does that do? So in this case, so we have this number. We're shifting by 2 bits. So we're going to add 0011 to it. And so what this is going to do is if there's any bits here in this bit that would have been truncated before, what's going to happen is adding this will cause it to show up over here. And so then instead of these bits being completely ignored and just thrown away by truncation, it will allow it to round. So when we do this, what we see is that we get 1, 0, and then we carry 1, 1. So we add the bias, and now we shift by 2, padding with 1s because it's an arithmetic shift. And we get 1, 1, 1, 1. These two got thrown away. These two got shifted over, and there's the padding. And so what's this equal to? This is equal to -1, which is what we wanted. So does it make sense how adding this bias allows us to round towards 0 rather than rounding down towards infinity by preventing us from just throwing away these extra bits if they're non-zero? And if these are 0, well, then adding doesn't really do anything because there isn't going to be any carry bit into the part that doesn't get cut off by the shift. Does that make sense to everyone so far? Yes? Okay. So that's a little bit of integer division. So a couple other notes about integers. So one of the properties of integers that we care about is endianness. So endianness says, well, which bit is most significant in a binary number? What order are these bits stored in memory? And you don't really need to worry about this quite yet, but very soon, once BombLab is out, it will matter because you'll want to actually make sure you're reading off the bits correctly. So what does endianness mean? So say we had a number. Does everyone have this written down if they want it? Okay, so say we have a number. Say our number is like 0x 1, 2, 3, 4, 5, 6, 7, 8. So we've got this 4-byte number, 1, 2, 3, 4 bytes. And we're going to store it in memory. And we want to know the difference between what it looks like in little endian and big endian. So in little endian, it's the least significant bits that are stored first in memory. So in memory, this is actually going to show up as the 7, 8, and then the 5, 6, and then the 3, 4, and then the 1, 2. And if you don't know that's happening, you'll get confused because you'll read this off as the numbers 7, 8, 5, 6, 3, 4, 1, 2, and that's not the same as this. In big endian, we store the most significant bit first in memory, and it reads off the way we normally would. However, the Intel systems that we'll be using, that are used everywhere, pretty much, do it this way. So in BombLab, you will have to worry about this and make sure that you are not accidentally interpreting it as a big endian number when it's little endian. So let's see, I think big endian is used by ARM. So if you're playing with your cell phone at the bit level, you'll get to see this, which is a little bit easier to read based on what we're used to. Okay, so does that make sense, little endian versus big endian? And you'll see that again very shortly in BombLab. Everyone's good? Okay. So then, another thing we have to talk about is floating point. So floating point numbers are quite a bit more complicated than just integers. Integers are great. Integers are they're discrete. They're easy to work with. We have bits that are discrete, so the translation between the two isn't too hard. Floating point numbers are a little bit more tricky because now what we want to be able to do is we want to be able to represent fractions in our systems. So how do we do that? So the main idea is that we have sort of a binary point. So this is like a decimal point, except for our numbers are binary, not decimal. And the bits to the left of this point, are your normal powers of 2, starting with 1 and going all the way up to however 2 to the I, however many bits you have. And then the bits to the right of the point are then the negative powers of 2. So 1/2, 1/4, 1/8, all the way down to 1 over 2 to the negative j, however low you go. And then this pattern, represents just the sum of powers of 2. So just like before with our integers where we had a sum of powers of 2, we have a sum of powers of 2 here. It's just that some of those powers of 2 are now negative. So there's a particular standard for floating point numbers that's used just about everywhere, and that's the IEEE standard. So there's 2 different main versions of this, the 32-bit version and the double precision 64-bit version. So those are what you would call floats and doubles in C. If you're using another language that has some sort of floating point type, it probably maps to one of those. So if you've used SML, the type real is actually just represented by a double precision floating point number. For those of you who've taken 150. So what are the difference between these two? So the difference between the two is just how many bits we have for each portion of the number. So the number is split into 3 different bits. So we've got 1 bit for the sign bit. This is the same as with the integers. If it's 0, the number is positive. If it's 1, the number is negative. And then we have, in the single precision, 8 bits for our exponent. In the double, 11 bits for our exponent. And then 23 versus 52 bits for the fractional component. So I'll talk about what that means shortly. But essentially what we're doing is we have some fractional component, and we're multiplying it by some exponent. It's like a scientific notation, if you're familiar with that. And then there's also another 80-bit standard that's not as standard because it's not used everywhere. It's just sort of an Intel-only thing that gives you even more precision than a double. But those aren't used too often. Okay. So yeah, so it's sort of like a binary scientific notation, like a simplified version of it. And we'll go over what it really is in a moment. But you're essentially doing the sign bit times the fractional component times 2 to the whatever the exponent is. So there's a couple other things in it. But here's an example. So you've got 3 exponent bits, 2 fraction bits, 1, 0, 0, 1, 0. And we'll get to it shortly, but first we should talk about how these things actually are. So first, let's talk about, there's 2 different types of floating point numbers. There's the normalized numbers and the denormalized numbers. And so we care about a couple different things. So we want to calculate a couple different values. So the first is m, which stands for mantissa. And this is going to be equal to 1 binary decimal point, whatever the contents of our frac section is. So back here, that frac, those frac bits, those go here, following a 1 and a binary decimal point. And then we've got e, which is going to be equal to the contents of the exponent bits minus a bias. And then we've got the sign bit, and this is a sign bit. And our floating point number is going to be equal to negative 1 to the s times m times 2 to the e. So this is the actual formula for calculating the value that a particular floating point number represents. So what is this bias? This bias is going to be 2 to the k minus 1 minus 1, where k is the number of exponent bits we have. Okay. So let's work out what that particular number represents. So we've got 1, 0, 0, 1, 0. And I said that k equals 3, so 3 exponent bits, 2 fraction bits. So if we look here, the first 3 bits are the exponent, and the next 2 are the fraction, and we don't have a sign bit here. So we've got 1, 0, 0, 1, 0. So this is the exponent. This is the frac. Okay. So what are these values going to be? So what's m going to be? This one's easy. For this example. Yep, 1.10. And base 2. And this is equal to what? This is equal to 3/2 in base 10. So it's 1 plus 1/2, the first place on the right-hand side of the binary decimal point. These are increasing powers of 2. These are the negative powers of 2. And then we have e. So what's our exponent? Our exponent is 1, 0, or 1, 0, 0, which is equal to 4 in decimal. And what's our bias? Our bias is 2 to the k minus 1. So we've got 3 exponent bits, so k is 3, minus 1 is 2. So 2 to the 2 minus 1. So that's 4 minus 3 equals 1. So m is 3/2, e is 1. We don't have a sign bit. We're assuming all of these numbers are positive in this 5-bit system. So what's the value of our floating point number? It's 3/2 times 2 to the 1 equals 3. So with no sign bit, 3 exponent bits, 2 fraction bits, 10010 is equal to the decimal number 3. Does that make sense how we got that? And sure enough, the slides agree with me that that's the answer. Okay. So we have a different thing too, though. So that was a normalized number. This is normalized. We also have what are called denormalized numbers. So these normalized numbers are great, but there's a couple problems with them. Can anyone point out one particular problem with representing numbers using this formula? There's one that's actually really important. So notice what we have here with m is 1 point whatever's in here. So that means there's always a 1 somewhere in our number. What does that mean about the numbers that we would be able to represent if we only had this? Yeah, we don't have 0. And 0 is kind of an important number that we want, right? 0 is a great number to have. So there's a separate format for denormalized numbers. So denormalized. And so with denormalized, what we're going to do is we're going to say m is actually equal to 0 dot whatever is in the frac bit. And the exponent is going to be negative bias minus 1, or negative bias plus 1. And then we're going to have the same formula here to actually calculate the value of the number. So now we can actually represent 0. Bias. Now we can actually represent 0 because we have a number that would be all zeros, and that's going to be 0. So we know that a number is denormalized when the exponent equals 0. Okay? And we know that a number is normalized when the exponent is non-zero and something else. So we're going to have to reserve a couple bit patterns to represent some special cases. Because floating point numbers can do more than just normal numbers. They also have special cases for infinity, for negative infinity, and for values that aren't a number. So for instance, if we try doing something like square root of negative 1, or if we try doing infinity divided by infinity, or 0 divided by 0, there is no number that corresponds to that value, so there is a special case of floats that will map to something called not a number, which signals that there just is no value that we can assign to this expression. So what we have for the normalized is that it's when the exponent is non-zero, and also the frac part is not all zeros and not all ones. So then the normalized has this implied leading 1. What's the corresponding part for the denormalized? What would be the right-hand side of this table? I wrote it on the board here. It's that we have an implied leading 0. That's the difference. And then here, we've got exponent minus bias. Here we've got the other way of determining the exponent. The normalized are denser near the origin, and they get more spread out as we get farther apart. Because what we're doing is we have this constant amount of precision for the fractional part, but this bias, this exponent, every time we increase it by 1, we've gone up by a power of 2. So we've gone up by a power of 2, but have this constant amount of precision here. So what that means is they're actually getting more spread out as we go towards negative infinity and infinity. The denormalized numbers are going to be evenly spaced. That's one of the properties of them. And then the normalized numbers are bigger numbers. I think I got this wrong. Should be 1 minus bias. So yeah, so the normalized numbers are large numbers, large in either extreme, numbers of large magnitude, and the denormalized numbers are the ones close to 0. And so whenever you're doing conversions between ints and floats and stuff, assume that it's going to be a normalized number until you have reason to believe that it's not, because most of them are. There's more normalized than denormalized. Okay, and then here's the special cases. So I was talking about some special cases. So if the exponent is all 1s, so all 1s would be 2 to the k minus 1, that whole exponent is 1s, then that's infinity. And so you can get infinity if you go above what can be represented by a finite number. So you can just keep adding numbers, and eventually once you get bigger than the biggest number it can represent, if you try adding more to that, it'll be infinity. If you try dividing by 0, division by 0 is infinity. If you divide a negative number by 0, that's negative infinity. If you divide a negative number by negative 0, that's positive infinity again. There is a negative 0. So 0 would be when all of the bits are 0. Negative 0 would be when the sign bit is 1 and the rest is 0. Negative infinity would be the same as infinity, but with a sign bit of 1. So all of the exponent bits are 1 and a sign bit of negative 1. And then we have not a number. So in infinity and negative infinity, all of the frac bits will be 0. If you ever have a case where you have the exponent is all 1s and the frac is something other than 0, then that represents not a number. And so not a number and infinity are two distinct things. Make sure that you remember that they're two distinct things. Infinity is overflow or unrepresentable because it's too big value. Not a number is something that there is in math, there wouldn't be a number that you could assign to this even if you had infinite precision. It's something indeterminate. Something's gone wrong. You've done an illegal operation of some sort, like trying to take the square root of negative 1, or something like infinity times 0, which is indeterminate. So another thing about floats. So floats, we have rounding rules. So imagine you have a bunch of data stored as floats, and you're going to, round it up to ints before you do something to it. If you had a case where, or I shouldn't say as floats, just imagine a statistical situation where you have a bunch of data and you're about to round it because you can't keep it at the full precision. If you have a bunch of stuff that ends in 1/2, and you have a rule that's either always round 1/2 up or always truncate or whatever it is, then you'll have statistical bias because all of the 1/2s will go the same direction and either push your average either up or down from what it really should be. So there's a different way of rounding, a more statistically sound way of rounding, and this is what floats use so that as we lose precision, we maintain some sort of, we don't have that bias as much as possible, and it's called round to even. So what it is when you have a number and you have to round it, and it's straight in between two other numbers, it's like halfway between them, you round to the one that's even. So if we have, say, 1.5, and we want to round this to a whole number, by round to even, what do we get? 2, right, because 2 is even. Let's say we had, though, 2.5, and we're going to round it, and we're going to use round to even. What do we get? 2 again, right. So even though if you had the more standard rule of 0.5 just rounds up, this would round to 3. But with round to even, you round to whichever side is even. And this is a good rounding scheme. And so you see here, in the normal cases, where you're not exactly halfway between something, you do what you would expect. If you're below halfway between, you round down. If you're above halfway between, you round up. But when you're exactly in between, you'll round towards whichever number is even. Okay. So how do we actually implement that? There's some rules. So you can look at the part that's right on the boundary of where it's going to be rounded. So you've got the last bit that's not rounded, the first bit that's going to be rounded away, and then everything below it. And so you take the OR of all of those bits, 2 to the end below what's going to be rounded, and you take the bit right below what's going to be rounded and the bit that's going to be the least significant bit once you do the rounding. And if you have 2 or more of them as ones, then you'll be rounding up. Otherwise, you won't. You'll be rounding down. So there's the table there. Okay. And so then we've got some examples here just to finish off the recitation. So, okay, so we're back to this 5-bit system, 3 exponent bits, 2 fraction bits. What's the bias? So I already calculated that before. So we had k equals 3, so that's 2 to the 2 is 4 minus 1, so the bias is 3. And then we can talk about, okay, what's the largest denormalized number that we can represent? Since we're running short on time, we'll put the answers up and we'll just look at them. So the largest denormalized number we could represent, the denormalized number is here, where the exponent bits are all 0, so the first 3 bits have to all be 0. And then to get as big as possible, we could have all the rest of the bits be 1. And so that gets us to 3/16 when we apply this formula. The smallest normalized number we could represent would be where this part is 0 and we have the smallest fraction possible. That's going to be 1/4. The largest finite number we can represent is going to be 14. Smallest non-zero number it can represent is going to be 1/16. So what happens if we have this system and we try doing 14 plus 14? What is the resulting floating point number going to be? Yeah? Positive infinity, right. So anytime we go over what's the largest finite number we can represent, then it just overflows into infinity. So here we have an additional table of practice problems. These are good ones for you to try out. But we're almost out of time. So I'm just going to put up the answers real quick. You should try these out and make sure that you understand why all of these work as they do. It's the same formulas we applied here, just working them out on different numbers, going different directions with them. So here you can see that 19, if we try representing 19, there's a case that's bigger than the largest positive number we can represent. We'll get infinity. Okay, so here's a recap of what we talked about. Same stuff I wrote on the board. Formula for floating points. Most significant bit is the sign bit. The bias normalized is when the exponent is not all zeros or not all ones. Denormalized is when the exponent is all zeros. If the exponent is all ones, that's one of the special cases. Normalized, we've got 1 point frac and exponent minus bias. Denormalized, we've got 0 point frac and bias plus 1, or negative bias plus 1. And then here are the special cases. We've got plus and minus infinity, not in numbers. And then you've got positive and negative 0. Always round towards 0. So any questions before we're out of time? Yes?
Just a minor thing about style on this assignment. I know that shifting by a negative value is undefined behavior.
Right.
But if we have code that works correctly and passes, that has a potential to shift by a negative value, but it doesn't affect it because on Intel doing that leads to a 0, is that all right? Can we submit that as long as BDD check says, or not BDD check, BDD check and driver.pl say it's okay?
So there's some assumptions that you can make about the behavior of the machine written in the bits.c file. But beyond that, what the BDD check does is, what it does. The BDD check is actually a symbolic execution. It doesn't actually run the code and execute it. So if what it's doing is passing, then you can use that, yeah. Any other questions?